Sokolovskii. We are recording. So we're going to have two speakers today, Pablo from the Polytechnic University of Madrid and Ilya Sokolovskii from the University of Jyväskylä in Finland. And it should be a very interesting day. So they will be telling us all about their current research projects and career paths as well. And we'll be available to reply to any questions you have during our Q&A panel session that will start after all the presentations have been delivered. So stay on your seats to give them all your questions. And our aim today is to promote a great discussion around the solar energy theme and promote wonderful research and cutting-edge techniques like the ones they are all using in their work. So with no further ado, let's introduce our first speaker. So our first speaker is Pablo Sánchez-Palencia Vallejo, final year PhD student from the Universidad Politécnica de Madrid, the Polytechnic University of Madrid, from Professor Pablo Palacios' group. Pablo obtained his MSc from the Polytechnic University of Madrid, where he also worked as a collaborator for an investigation project focused on the use of ab initio calculations for the characterization of perovskites applied to solar cells. He is now carrying out very interesting research using density functional theory, DFT, and machine learning techniques that focus on exploring the configurational space of spinel nitrides, predicting some of their optoelectronics properties like the band gap. So Pablo, the stage is yours. You can share your screen and let's hear from your wonderful work.
Thank you so much, Anna. Okay, so can you all see the presentation correctly?
Yes, perfect.
Okay, so thank you. Good morning, everybody. I don't like much to speak about myself in here, but I think it's pertinent in here to give a brief introduction about who am I and which is my career path. So I'm going to start, as I say, with a brief introduction in that sense. As Anna said, I'm a PhD student and assistant teacher at Universidad Politécnica de Madrid, where I also did my bachelor's master's degree. Specifically, I did a bachelor's degree in energy engineering and then a master's on solar energy in the marvelous Solar Energy Institute, which is one of the oldest research centers in the world devoted just to solar energy. So as you can see, my background is quite aligned with the topics of this webinar series, and in particular with this one, of course. It was during my master's that I had my first contact with material science and computational chemistry. And I like it so much that I decided to change field from the most applied of science, engineering, to do fundamental research during my PhD. When I was starting in this completely new field for me, I focused on the application of density functional theory to the search for new absorber materials for photovoltaics. After a few years, as lots of people in the field, I decided to start implementing machine learning in my workflows to basically optimize that search and be able to explore bigger chemical spaces. In that process of search, a few candidate materials I usually or ideally found as result. However, in more cases that we'd like to admit, those results are kind of abandoned and never become real applications, which is the key point at the end. In my honest opinion, this happens because in many cases our theoretical calculation doesn't reflect what is later found in experimental labs. And that doesn't mean that our calculations are not accurate, but that we are simulating ideal solids. And in real life, solids are far to be ideal. In fact, they are full of disorder and defects. And that was the key question that I wanted to bring here today. can we also use the huge potential of machine learning to study disorder and defects in solids and not only to perform broad searches in big chemical spaces? And my answer in this case is a clear yes for disorder, as I will show you in this presentation. And I haven't tried yet, but I think so in the case of defects. So the project that I'm presenting here today, as I said, is focused on the study of disorder. So I think it could be expanded to include also defects with time and resources. In particular, we have used machine learning to study the configurational space of Spinel nitride solid solutions in a project that has been done during a 4-month research stay done in the University of Reading. So moving to the topic, let's start by introducing the materials we are studying. The standard Spinel structure is formed by a cubic closed packed lattice of anions, where the cations occupy just part of the octahedral and tetrahedral sites formed by that lattice. There are twice more octahedral than tetrahedral sites, and you can see in the formula with B and A. And the peculiarity of these nitrides in comparison with the traditional oxides when we talk about the spinels is that both their cations have the same charge and therefore are easily interchangeable between the two cationic sites, leading to very interesting studies. This family of materials present a series of very interesting properties, which are listed here, but I will just stop by the last two, which I have to explain. First, the combination of coordination environments that I already introduced, which has already been proposed as a very good compromise formula between the good defect tolerance characteristic of octahedral systems, like for example, perovskites, and the superior long-term stability more typical of tetrahedral systems, like for example, silicon or 3-5 semiconductors in photovoltaics. The other property that I wanted to explain was that they present a highly tunable bandgap. As we can see in the graph, just by changing the concentration of cations, we can move in a very wide range of bandgaps. And in this project, we will just focus on tin and germanium nitrates, which corresponds to the yellow line, which exhibits the most adequate bandgap range for photovoltaics. Focusing in this configurational space, which is defined as all the possible distributions of cations over the structure, we will be studying two main properties, the mixing energies and the bandgap values, which will be computed with DFT for a small fraction of all the structures in the space, and then predicted for the rest of them through the use of machine learning. We saw that the general formula of Spinel is this one that adjusts to our case with tin and germaniums in this way, where there are two main parameters, which are the X, which is the partial concentration of cations, and the Y, which is the inversion degree that describes the occupation of the cations over the two different kind of sites. That way, the whole configurational space is shown in this table, where the total number of configurations aggregated by relative concentration and inversion degree are presented. In this presentation, due to time limitations, we will only present the results of corresponding with a fixed concentration, so all the rest of the configurational space has also been explored. For this case, a bit less than 24% of all the possible structures have been computed with DFT out of a bit more than 4,000 configurations. In this slide, a brief summary of the computational methodology that we have used is presented. Firstly, a PV plus U functional has been used for initial structural relaxations, and then HAC06 hybrid functional has been used to obtain accurate bandgaps, trying to overcome the underestimation of this property that the first step commits. We have also used 56-atom conventional cells for our simulations to being able or to have more flexibility in the concentration levels and inversion degrees. And in the chart below, a comparison between our results and some experimental ones for the two binary compounds taken as reference is presented. We see that a very good agreement between both in terms of lattice constants and band gaps are presented, and then the methods that we selected are justified. As I was saying, we will be studying two properties. First, the mixed information energy as a measure of the relative stability of the different configurations, and then the band gap, for which we have to face the issue of the high cost of HSE calculations, considering it's the only way to obtain accurate band gaps. For that reason, and trying to avoid doing many of those calculations, we try to correlate the results of our previous step, here referred as GEA, to the HSE band gaps. And in fact, we obtain really good results, to some extent kind of unexpected, that allow us to reproduce those HSE band gaps with just a 1.4% of the whole space computed with HSE. And therefore, we will be using GEA band gaps after correlation in the rest of the study of the work. Moving to the machine learning part, we have tested different structural descriptors, which are the way the structural information used to obtain the desired properties is encoded to the models. In here, the three of them for which we obtain the best results are presented. First, the Coulomb matrix, which describes the electrostatic interaction between atoms, considering the atomic number of the different species and the distance between atoms. The many-body tensor representation, which also takes in similar information, but sequenced in a very different way, more destined to visualization and on those things. And finally, the cluster correlation function, which are the most different ones, as they don't consider the species we are using. Instead, they represent the site occupation in a binary way over different atomic arrangements or combinations that are called clusters. Apart from those descriptors, we have also tested different machine learning models. First, a very simple linear regressor with regularization, and also two more complex models, which are a gradient boost decision tree and a multi-layer perceptron, which is a kind of neural network. To rigorously measure the performance of those models and descriptors, we have used a small subset of configuration not used for training, which accounts with 20% of the size of the total number of structures computed. And for those, we have applied the mean absolute error as metric of performance. We can see that the cluster correlation functions are the best performing descriptor for both cases by far, which was an also kind of unexpected result, considering that in some previous studies, the Coulomb matrix usually performed better, at least for the case of the band gap. Regarding the models, the linear regressor is enough to achieve a very good description of the mixing energy property, while for the case of the band gap, the multi-layer perceptron seems to capture better the more complicated physics behind the pattern structures that describe this property. In these graphs, where machine learning predictions versus DFT calculations are presented, also two other metrics are shown, the maximum error and the coefficient of determination, which are also very good for both cases, for both properties. Apart from evaluating the performance of our models, we wanted to identify how the models gave the predictions and which way they used to give their predictions. And for that, we perform an analysis of the importance of the different features introduced into the model, which in our case, using the cluster correlation function as the best performing descriptor, were the different clusters in the functions. The clusters are enumerated and also characterized through two parameters, which are the K and L that are defined there. The K represents the order of the cluster, which means the number of atoms involved in that clusters, and the L is the maximum distance between those atoms. we can see how for mixing energy, the cluster one is the most important one by far, as we can see in the width of the graph. And this cluster corresponds to the individual clusters that defines the octahedral occupation, meaning that as we are working with a fixed concentration, it would be analogous to the inversion degree of the configuration. And therefore, we can say that mixing energy is mainly described by that parameter, and to a lesser extent by some clusters of lower order. As you can see, most of them are of order 2. On the contrary, for the case of the bandgap, the importance is much more distributed between clusters, being the most important ones of the higher order considered, which is order 3. That illustrates the higher complexity of this property, which is dominated by more extended structural motifs than the mixing energy. Apart from once we have proved the good performance of our models and therefore our results, we have generated a configurational map of the whole system where the singular structures have been identified, like, for example, those with the lowest mixing energies or the highest or lowest band gaps. Apart from that, also some trends can be noticed in the graph, in the map, like, for example, that higher inversion degrees are clearly energetically favored, which means that thin atoms occupy preferably tetrahedral sites. There's also a weak inverse correlation between mixing energies and therefore inversion degrees and band gap, which leads also to higher band gaps being energetically more feasible. Apart from that map, we have also performed a complete thermodynamical analysis where we have computed the entropy of inversion of this configuration of these spinels through the following formula. With that, we have obtained the free energy of every configuration and perform Boltzmann statistics to obtain equilibrium properties at different temperatures. Following that procedure, we have obtained the equilibrium inversion degree shown in the graph at different temperatures and compared it with a more traditional model, which is called the 3-point model, which is much more cheaper than our case, but at least here not very accurate, as we can see. Because the decrease in the inversion degree is much more pronounced with our model than in the previous one. That means that if we could freeze in some way the disorder characteristic of higher temperatures with some synthesis technique, like, for example, rapid quenching, we could be able to fine-tune other properties related with this inversion degree, as, for example, as we saw, the band gap. This way, we could obtain a bit higher band gaps, a lower band gap, sorry, through this technique or through this process. In conclusion, we have achieved an accurate description of the whole configurational space with very good metrics of performance and at a greatly reduced cost of computational resources. We found that the cluster correlation functions were the best performing descriptor for this system. And depending on the property that we want to predict, we may need different models, more simple or more complex, and even we will need to expand the basis of the clusters in the cluster correlation function. Finally, we have used our results to generate a configurational map from which we have extracted some knowledge, some interesting knowledge, and we have also performed a thermodynamical analysis that help us to outline a route to fine-tune different properties like the band gap through different synthesis processes. To conclude, I just wanted to acknowledge all the funding received and also all the help and support received from my supervisors. And I finally leave you with this slide where you can find some of my contact details and information about our research that we perform in our group. And of course, I will be glad to answer any question that you may have in the later Q&A session or panel session. So thank you so much for your attention.
Thank you, Pablo, for this wonderful talk and for sharing your work with us today. was great to see your machine learning results and predictions. Thank you.
Thanks to you.
So now we're going to be hearing from our second speaker. So our second speaker is Ilya Sokolovskii, second-year PhD student from the University of Jyväskylä in Finland, from Professor Gerrit Groenhoff's group. And Ilya obtained his MSc from St. Petersburg State Electrotechnical University, having also previously worked as a laboratory assistant at the Youth Institute for 1 year. He's now focused on studying polariton propagation in organic materials via atomistic multiscale molecular dynamics simulations for his PhD in Finland. So, Ilya, if you're ready to share your screen with us, the stage is yours, and let's hear about your work. Thank you.
Okay, let me share my screen. Okay, can you see it?
Yeah, it's perfect. Thank you.
Okay, so thanks a lot for introducing me and letting me attend this webinar. Well, I would like to share with you the results of our research group on the computational study of energy transport in organic materials under strong light matter coupling. And before I start telling the story, I would like to acknowledge people who worked on this project. As you already mentioned, it's my supervisor, Gerrit Groenhoff, and the leader of our research group. And also Ruth, she used to be a part of our group, but now she works in the University of Madrid with our collaborator, Johannes Feist. And in the beginning, I would like to say something that you probably know much better than me, namely that the global photovoltaic market is currently totally dominated by silicon-based solar cells, which take more than 90% of the global production. And the technology is well developed, and the efficiency laboratory made silicon solar cells approaches its theoretical limit, and there is almost no space for further improvement. So people search for different ways of how to go beyond this limit. And among proposed ways, there are, for example, construction of multi-junction solar cells to cover as more solar spectrum as possible, or to increase somehow the external quantum efficiency, or to concentrate sunlight. Also, people try alternatives to find alternatives to silicon, like for instance, A3B5 materials, cadmium telluride, perovskites, etc. But here I would like to pay attention for organic solar cells, which are cheap, easy to produce, and flexible, and they potentially can fill their niche in the global PV markets. But there is a problem. Well, I'm sure you all know how solar cells work, but I just would like to quickly mention that any solar cell must do two basic things. First, to absorb sunlight, and unlike conventional inorganic semiconductors, which are crystals having their band structures, organic materials consist of separate molecules in which absorption of sunlight leads to promotes electrons from highest occupied molecular orbital to the lowest unoccupied orbital, and this leads to creation of bound electron hole pairs, or excitons, and those excitons are responsible for the photogenerated current in organic materials. And the more light is absorbed, the more excitons there are, which means that if we make our solar cell too thin, we'll get negligible photocurrent. So the requirement is to make it as wide as possible. However, we also need to bring the emerged charges to electrons. So if the solar cell is wider than the diffusion lengths, which determine the efficiency of this separation, we will get almost no photocurrent, because in this case, excitons will not be capable of reaching the electrodes. So the diffusion length sets the upper limit on the width of solar cells, and we need to always find a compromise between absorption and diffusion lengths. And unfortunately, in organic materials, excitons propagate by means of hoppings between neighboring molecular sites. This process is very ineffective and slow, and is hampered by thermal disorder. As a consequence, for most organic materials, diffusion length is just a few nanometers, which is not enough. And as a result, the efficiency of even the best laboratory produced organic solar cells is much lower compared to silicon-based counterparts, let alone the commercial made models. So the problem is how to increase the energy transport in organic materials. And it seems like it might be done by strongly coupling excitons with light. But what is strong coupling? Well, let's first consider interaction between a photon and an excitons in free space. Well, when they are at resonance, the interaction leads to absorption and creation of an exciton. And after some time, it leads to emission of light, and the photon just goes out of the molecule. This is called weak coupling, and this is quite boring. But what if we, for example, take a cavity? In the simplest case, it is just two parallel metallic mirrors. And in this case, the light might be trapped between the mirrors for some time. And if there is a molecule between mirrors, the light will be absorbed, then again emitted. But now the cavity will not let it escape. Instead, the light will be absorbed again and then emitted. And this process of absorption and emission will keep repeating for some time with a so-called Rabi frequency. And if this Rabi frequency is higher than decay rates of both the exciton combination and cavity leakage, the system is thought to be in so-called strong coupling, under which two new hybrid states, which inherit properties of both excitons and photons, emerge, and they are called palagetons. Upper palageton with high energy and lower palageton with lower energy, and they are separated by an energy gap called Rabi splitting. This is for just one molecule and one photon, but if we take a lot of molecules with the same transition energies, we will again get the upper palageton and the lower palageton, plus a lot of so-called dark states, which, although have the same energies as bare molecular transition and no contribution from light, they're not just bare excitons. Instead, they're hybrids of all the molecular excitations which participate in strong coupling. And currently, it seems like those dark states play a crucial role for the dynamics of palagetons, and we should keep this fact in mind. One more important thing is that every cavity supports many modes with different frequencies, and they have dispersion, meaning that the energy depends on the direction of light or the wave vector. And also, so the palagetons also have dispersion, shown here in blue and red for the upper and lower palagetons respectively. And those palagetons also have the group velocity, which is determined as the derivative of energy with respect to wave vector. And it turns out that this group velocity can reach from units to 10% of speed of light, which is enormous. And why wouldn't we use these facts to increase energy transport and to check whether it's possible to go beyond the diffusion lengths in organic materials? And to do so, we simulated the excitation transport in an ensemble of molecules inside the cavity. And this is a quantum system, so it can be described by a wave function whose square would give the probability density of finding the excitation in space at each moment. And initially, we set the wave function manually in order to mimic an external laser excitation. But then, to obtain a wave function at any later moment, we need to solve Schrödinger equation with the Hamiltonian including the ground state and excited state energies of each molecule in the cavity, as well as the energies of photons in cavity, and the interactions between all molecules and all cavities, cavity modes. And since we would like to consider many molecules and many modes, we just can't solve this problem in a fully quantum manner, at fully quantum level, because it's just too computationally expensive. As an alternative, we could apply molecular dynamics, which is based on solving classical equations of motion for each atom. But the problem is that molecular dynamics do not account for quantum effects, so it is not capable of reproducing excitations correctly. So we need to find a trade-off between quantum and classical approach. And there is one nice method implemented in Gromac's molecular dynamics package, which we used in this study. And this approach does give this trade-off. And it's called quantum mechanics, molecular mechanics approach. And based on the fact that the important processes in molecules, like, for example, excitations, occur not in the whole molecule, but in a part of it, which means that we can separate each molecule, which are rhodamine molecules in water solution in our case, into a classical subsystem treated with molecular force fields just classically, and quantum subsystem, which is treated in a quantum level. And in this study, we used Gaussian software to calculate both ground and first excited states for each molecule, an ensemble at each time step. We also modified the Gromac's code in order to add cavity dispersion and to place molecules in a chain between the mirrors of the cavity. In total, we have 1024 molecules and 160 modes, which is quite a lot. And for each cavity modes, we included the decay rate in order to make it more realistic. So experimentally, there are two ways of how to excite the polygons. And the first way is to do it indirectly or off-resonantly. In practice, what people do is to excite a molecule up to one of its high energy states, which then quickly relaxes to the first excited states. From there, population can either decay to the ground state or to populate upper and lower polygons. And we simulated our system under this excitation. And what we see is that initially the excitation is localized just on a single molecule, but then the polygon wave packet is formed and it starts to propagate, covering the distance of at least a few micrometers, which is a few orders of magnitude higher than the diffusion lengths of bare organic materials, which is just a few nanometers. But why is this happening? Well, when we excite the molecule, the population starts to transfer to the polygon branch at different wave vectors, thus creating polygons moving with different velocities according to their dispersion. And the wave packet is created and it starts to spread, covering a micrometer scale per distance. But there is the reverse process of energy transfer from the polygon branch to the dark states. And as we remember, since there are a lot of those dark states, they effectively trap polygons, and this prevents polygons from their free ballistic transport far away from the initial excitation. As a consequence, even after 300 femtoseconds, the top of the wave packets remains quite close to the excitation spot. And if we look at the mean square displacement of the wave packet, we will see that it follows a linear dependency, which indicates the diffusive-like process, diffusive-like transport. Then, if we include a cavity decay, the propagation would be suppressed, but still of the micrometer range, and the MSD is still linear, indicating diffusive transport. But what is also important is that polaritons can survive for much longer than it's described by the cavity lifetime, which is just 50 femtoseconds, but we see that there is signal even after 300 femtoseconds, and it will survive even for longer. Yes, and it is seen in the population plot of the ground state. So we can see that after 100 femtoseconds, there are more than just about 20% of the ground state populated, while from the for cavity, it would be just gone. And this is due to, again, dark states, because they trap polygons, and in such a way they extend their lifetime. And this is why people experimentally observe polygons even after a few picoseconds. Okay, the second type of excitation is resonant, and probably this is more interesting because in resonant excitation, the polygons are excited at different energies, and it's kind of that what we expect to see in solar cells, because the solar spectrum is broad, so we would see excitation of many polygons. So what we did here was to create a Gaussian wave packet of the lower polygons, with the center corresponding to the maximum growth velocity. And again, we see how those polygons propagate. We see that the packet spreads, covering again micrometer distance, just in the case of indirect excitation. And this is true for both perfect cavity, it is without decay, and for lossy cavity. And important finding is that in the beginning, the mean square displacement is quadratic, meaning that the transport is ballistic. It is without energy losses. This is because initially we created polygon wave packet, which moves exactly with the growth velocity. But then, since the polygons start to transfer to the dark states and trapped by them, the photonic contribution to the wave function becomes less than the molecular contribution, and this leads to the emergence of the diffusive transport, like we observed under off-resonant excitation. Yes, in summary, we studied polygon propagation by means of quantum mechanics, molecular mechanics simulations, and the most important of magnitude higher than in typical organic materials. And also polygons can survive for much longer than expected from cavity lifetime. And we believe that this finding will help to rationally design molecular cavity systems to achieve coherent long-range energy transport in solar cells. But the main question is how to do this in practice. And actually, this is the goal of our future study. Yes, I think that's it.
Great. Thank you very, very much, Ilya, for a wonderful talk. It was nice to hear about your work, especially about organic materials. That's quite interesting.
Yeah, thank you.
Right, everyone. So now we will be opening our Q&A panel. So our panel is the opportunity for anyone in the audience to ask questions to our speakers, either about their research work or about their career path as well. So you can type any questions you have on the chat, or if you want, you can raise your hand and open your mic, open your camera to ask things out loud, whatever you prefer. Me and Rihanna will be reading the questions from the chat to our panel. And in the meantime, while we wait for the first questions, I would like to ask the first question. So considering that a great part of our audience today is made of first-year PhD students, so PhD students who just arrived at the university now in September, I'd like to ask you both, Pablo and Ilya, if you could give one advice to someone starting their PhD now, you guys who are already like in the end or in the middle of your PhD, yeah, what would you say to them from the beginning? What would be your advice to our new PhD students?
So I may start as I speak first. I mean, there are many advices that could be given to people who's starting, as it's a long journey, and most of the cases you don't know much of it until you are completely into it. But I would say that the most important one, in my opinion, is that there's no need to hurry up things. I mean, for sure there's a due time, but it's a long journey, as I said. And I think it's quite important, at least for a long career, if you want to stay in academics, especially, it's very important to establish solid foundations. So to don't stop formation and learning everything related to your topic, even if that implies to deduct some time from the obtention of results in your project.
Great, thank you, Pablo. And Ilya?
Yeah, well, from my experience, when you start PhD, you do not understand a lot of things, so you have to read a lot. You have dive into some papers, but there are also many people who understand your topic much better than you. So my advice would be to not be afraid of asking maybe stupid questions and to be curious. Yes, and maybe also to try to jump at the chances that you are given. Like if you are offered to participate like in a workshop or somewhere else, just do it. Yeah.
Great, guys. These are all awesome advice. Totally agree. Maybe I'll give mine. I'm also a PhD student. So as you both said in the beginning, you need to build a solid foundation. And that means reading a lot. And at the same time, as Ilya said, don't panic if you don't understand everything, or even if you don't understand anything, because that's what the beginning is for. The first stage is panicking. Second stage gets a bit better, and so it goes on. So great, guys. Thanks for your advice. And so our audience is still shy, unless there is anyone who wants to speak out loud. If that's the case, please raise your hand or put your mics on, and we can put you online with our speakers. If not, let's have some more science-themed questions then. And audience, please don't be shy. So, all right. So, Pablo, I have a question for you then, while our audience is warming up. So one of the things you said, which was very interesting, is that the models that you use, depending on the property you want to focus on, like there is one model that's best for one and another model that's best to the other one, yeah?
Yes.
So is there like do people know why that is the case, why one model is best for that and the other one is best for that, or was a surprise? How was the process of finding that out?
I could say that there's some, let's call it knowledge or intuition, but at the end you have to try it, because it's something that can change from one system that you study to another. And I have to say that I don't have a very long experience in machine learning, but as far as I have seen, in our case, it was kind of unexpected to find that, for example, the cluster correlation functions were performing better, and we get to know that by trying different models and different descriptors. So I think, yeah, that's a very important thing when implementing machine learning is to try not only different models, because within the model you also have to parameterize some things within the model, and that's quite important. So you have to test many of those parameters and many of those models to find the best performance.
Yeah, thank you. And how long did it take you to, like, from the beginning of testing the models until you get your results, just so our audience can have an understanding of how long does the training and choosing the models for a machine learning project takes?
Okay, it was not that much, to be honest. The process step by step in this project was firstly to get done all the calculations, which took I would say almost 2 months or 1.5 months or so. And the good thing is, once you have programmed all the calculations to be launched in your system, you have time meanwhile to be preparing or be starting to compute or to program, to code all the models and all those things. So once I had the results and I had to do the test, it was not that long. It was I would say 2-3 weeks maybe. Quite intense, because you had to try a lot of things and be ready to change the parameters once the calculation is done and all those things, once the testing is done. But it was not that long.
Thank you. And so let's check our chat. We have a question to our audience members. If anyone has any research link with Pablo's or Ilya, so people from the machine learning groups or people from the MED calculations, or anyone from solar energy, really. If you want to shout out and talk about your matters, you're more than welcome to. And right, so, okay, so now Ilya, I do have a question while our audience still warms up, and we do have a raised hand. Rhiannon? Yeah.
Yes, I was just wondering, Pablo, is there any sort of training or research courses that perhaps someone who's a beginner to machine learning could, go online and find, or is there a sort of course that you took, or did you sort of learn more from yourself? Just thinking, in case anyone here is completely new to machine learning, there might be a beginner's course out there that would be really useful.
Okay, I think there's a lot of resources out there on the internet, and for introductory courses, most of them are perfectly valid. But the only way to learn, I think, is to implement the model. So for me, the most complicated part is to find a project in which you want to work and that you have time to work on that and resources. Because there's also an alternative that you can use repositories or already prepare a machine learning project. Nowadays, many projects that are published need to be open source, open data. For example, all the project that I've been presenting today, it's all the code, all the resources are available, so you can go to the paper and download all the resources and try to perform some test on that data set. But I think only a course is not enough. You can get the main ideas, but the best way is to practice a bit.
Right, thank you, Pablo. Thank you, Rhiannon, for your question as well. Nice. So while we wait for questions, Ilya, I would like to ask a question about your work then. It was lovely to hear about work. I do molecular simulations with MD as well, so I was quite excited to see that in your work. So that's quite nice. And for me, again, my simulations are on batteries, not on solar cells, so it's a bit different. But while you were talking about solving the Schrodinger equation and all that part, I was just wondering, like, if any parts of your next steps, do you think about using density functional theory, DFT, to do, I don't know, some calculations with that, or no? So what are your next steps? What are you aiming for your final year?
The reason why we still do not use DFT is that because we would like to simulate as many molecules as possible to make kind of bridge between the experiments and theory based on some quantum stuff, because now there is a huge gap between the experimental results and what theory shows. So the molecular dynamics could help to make this bridge. So that is why we use quite a lot of molecules, but the price we need to pay is a lower level of theory. For example, in this study I showed, we used restricted Hartree-Fock for the ground state and configuration interaction for the excited state. Of course, we could use a better theory, but in this case, we would have to just simulate a bit smaller ensembles, well, much smaller ensembles.
I see. Yeah, it is the price we have. We end up having a panel, for everyone who doesn't know, of 2 PhD students who are computational based, yes, and a chairperson, me, who is also a computational person. So for anyone who's not in the area, it is indeed the price we have to pay when we want to do our calculations. The better the theory you use, the better the calculations you do, the more expensive the computational price is. So yeah, we are all suffering together. Wow.
Maybe I also have a question to Pablo.
Yeah, sure. Go on.
Sure.
Yeah, I've never heard about those materials before that you told about, but as I understood, they have quite high band gaps, starting from about 1.66 V, and I'm wondering. It seems like if we use them alone, we will just lose a lot of solar spectrum. So are they meant to be used, for example, in combination with silicon?
Yeah, the initial idea of a study of this material it was just exactly because their gap, it was a bit higher than the optimal for solar application, for photovoltaics. The idea here is, I don't want to extend much about it, but in our group we do a lot of research related to intermediate band solar cells. I don't know if you have heard about it. It's a concept where you introduce states inside the gap of the material that in theory could be used to excitate electrons in 2 steps. The thing is that for that configuration, a bigger band gap is required, but we do an initial study with these materials, and we found that the basic band gap, even before introducing those states, those defects, were interesting enough to do a study alone on them, and that's why we started with those. And the application would be not fixed. It could be for that idea, as I was explaining, but it could be also used for tandem configuration. As you were saying, it would make not much sense to use them alone, as a lot of solar spectrum will be lost because of the higher band gap.
That's okay. And also, those materials remind me a bit of perovskites, and as I understood, the obvious advantage here is that they're thermally stable, in comparison to perovskites, so they would be better. But what about the defects? Are they shallow or?
Yeah, I mean, we haven't performed a complete study of defects, but as I was saying, we did a previous study introducing those defects, trying to obtain an intermediate band solar cell. And for that goal, it was okay. The material were perfect. Were optimal to host an intermediate band. To be used alone, I would have to perform a different study that I haven't done, to be honest. So I wouldn't know if they would be appropriate in that sense, but it could be really interesting to study also the defects in the pure material.
That would be nice. Thanks.
Great. Thank you, Ilya, for your questions, Pablo for your answers, and thank you everyone as well for attending. Because of the time, with that, we will be concluding our Q&A session and panel and webinar. And I would like today to thank greatly, very much so, our speakers, Pablo and Ilya, for supporting our webinar and giving their time to come here today with us and share their amazing research project with us. So thank you so much. It was wonderful to hear about you both and about your projects, and see you guys discussing here at the end as well. It was quite exciting. So thanks so much for explaining your works for us. And also like to thank the audience for participating and coming together with us for this Solar Energy Day. And also I'd like to thank the Center for Energy for supporting this idea and curating this webinar, especially Rihanna, who is here with us today. So thank you, Rihanna, for your help. And for audience, if you're interested in our next webinar episodes, which will focus on other energy sources such as hydrogen and batteries, that they will be me. Please leave your email in the chat or send us an email in the Center for Energy. So you can be added to our exclusive mailing list for all the details about our next events. And also, since we are all here, next Wednesday, midday, midday, UK time, we'll have the first episode of our new series, which is Energy Justice and Ethics, on the topic of energy races with Dr. Trevor Nagani from the University of Johannesburg. So it must be a very interesting day next Wednesday as well. And also for everyone who's a PhD student based in Newcastle or who is willing to come to Newcastle, I'll be giving a talk next Thursday, the 20th of October, about everything I wish I knew before I started my PhD. So giving tips and, you know, just general PhD life advice to everyone. So everything that I thought it was helpful for me, hopefully will be helpful for new students as well. So if you're interested, send us your email in the chat or enter in contact with us with the Center for Energy social media or website. Shout out to us and you will be sending all the details to you guys. Yeah. So to everyone, thank you very much for coming. Thank you our speakers again, Rhiannon. And yeah, to everyone, I hope you have a wonderful Wednesday and I hope to see you again soon. Bye guys, thank you for coming.
And thank you,
Thank you so
Anna,
much,
for
Anna,
sharing.
for organizing and for the invitation.
Bye, thank you.
Bye all.